Swayam Prabha. Digital India. Educated India.
So, last class I was discussing about the bearing capacity of two-layer soil. Now, I discuss about that if the bearing capacity of the two-layer soil in the case 1, when the first layer is a stronger layer and the weaker layer is a and the second layer is a weaker layer. Okay, and then I discussed that how the loading is acting, and then because that means the bearing capacity you are getting from the contribution from the second layer, that is the QB, then the frictional resistance that we are getting due to the movement of the soil within the first layer, and that friction resistance we are getting by using these equation, and then we are subtracting gamma 1 h. Why gamma 1 h? Because during the QB calculation, if we take the contribution of the df and the h as a surcharge, but as the h layer contribution or h portion contribution already been taken during the shear resistance calculation, then it is recommended to neglect that contribution during the QB calculation. Okay. So, or it can be subtracted directly in the basic equation. In such case, we have to consider the both H and DF for QB calculation. Okay. So, now if I further simplify this equation, that now my if I get the horizontal component of del is acting here. Now, what is the passive pressure we have to calculate. So, now this is my the say second layer and this is the first layer, okay, and the first layer is here and this is df and this portion is h. Now, I have to calculate the passive resistance at this zone. Okay. So, passive resistance will be something like that. This will be the passive resistance at this zone. So, at say df point at a depth df, what is the passive pressure? The passive pressure will be gamma 1 df into Kp. Okay. So, gamma 1 and df is the depth of foundation. So, Kp is the coefficient of passive earth pressure. Kp is the coefficient of passive earth pressure. Okay. So, now at a depth of df plus h, because here you are getting basically the passive resistance from here to here. So, this is this passive resistance I am trying to calculate. Okay. Okay. This is at a depth of df, this is at a depth of h plus df. So, that means my sigma p will be this value and here sigma p, or actually this is sigma effective, but here the water table not considered. So, I am considering effective and total are same. So, this value will be gamma 1 df plus h into Kp, that is the pressure. So, this is a trapezoidal. Okay. So, here my contribution is gamma 1 df Kp, and here it is gamma 1 df plus h into Kp. So, now the total passive force Pp, total passive force will be half into this gamma 1 d1 df into Kp plus gamma 1 df plus h into Kp into h, because this is the into into h, because h is the thickness of this layer. So, finally, I can write that this value will be half, we can take h gamma 1 and df outside, okay, and we can take gamma 1 and 1 h and then another h outside. Okay. Let me first take that one. So, that will be this h I am taking. So, that will be df Kp, or Kp also I can take outside, because this is the df plus df plus h. So, that is into Kp. So, that will be equal to half gamma 1 h 2 df plus h into Kp. Now, if I take h outside also, then this will be half gamma 1 h square. So, I can take 1 plus 2 df divided by h into Kp. Okay. So, this is the total passive force which is acting. So, this is the total passive force which is acting, okay, and which is actually acting at angle of delta. So, I should write in this way. So, this is the total passive force, and that I am calculating by using these expression. Okay. So, now if I put these values, so now I have calculated that Pp is equal to half gamma 1 h square 1 plus 2 df plus by h into Kp. So, now if I put these values here, so I can now write that Qu, your Qu is Qb, then plus this is 2 Ca h by b, that is 2 Ca h by b, plus that Pp part I have to consider, that Pp is this equation, that is 2 Pp then 2 Pp tan sin delta by b. So, 2 Pp sin delta by b minus gamma 1 h. But remember that when I am writing gamma 1 h, actually we are taking that phi 2 equal to 0, because for the time being we are considering that your phi 2 equal to 0. That means, it is a your second layer is clay layer. So, now if I put this value Qb plus 2 Ca into h divided by b plus 2b, Pp is half gamma 1 h square 1 plus 2 df divided by h into sin delta into Kp sin delta into Kp sin delta minus gamma 1 h. Okay. Now, this sin delta, this Kp part we are now converting and we are writing that Qb plus 2 CAH by B plus 2 is cancel out. Now, this will be gamma 1 H square, then 1 plus 2 dF divided by H into Kp divided by B, and then we are taking tan delta. So, it is a tan delta. So, that means we have to multiply with cos delta, then gamma H. Okay. So, we are taking sin delta and then that we are writing in this form. Okay. Now, we are writing that Kph is equal to Kp cos delta. Okay. So, that means this is basically we are writing what is Kph. Kph is the horizontal component of passive earth pressure. Earth pressure coefficient. So, that means as I mentioned, if you look at these equations, so here your Pp is acting with an angle with delta. So, that means it has one horizontal component and the vertical component. Similarly, the earth pressure is also represented in this way, that the Kph is the horizontal component of the earth pressure, because Kp is that the total component or the resultant component you can say, which is acting an angle delta. Now, if I take that cos delta, then that will give you the horizontal component, and so that Kph is giving that coefficient which will give you only the horizontal component, okay, not the vertical component. Remember that it is not the resultant. Kp is the resultant part, Kph is the horizontal component of the earth pressure coefficient, because this is way all the charts are developed, where this Kph is considered, okay, the horizontal component. So, this way I can finally write that Qb plus 2 CAH divided by B plus gamma 1 H square 1 plus 2 dF by H, then this is Kph tan delta divided by B minus gamma 1 H. So, this is the expression, final expression will be this one. Okay. This is the final expression for two layer case. Okay. So, now so we have represented them in this way, and this way all the charts are produced. So, that is why it is taken Kph, not the Kp. Okay. If you take Kp, then it will be sin delta. If you take Kph, then it will be tan delta. Okay. So, now it is Kph. Now, as I mentioned, the delta is the angle between the soil versus soil. So, basically it will be the sin theta, I mean it will be the phi. Okay. So, that is why we can write that Kph is further written as Kph tan theta is a Ks tan phi 1, because it is soil versus soil. In this layer it is soil versus soil. So, that is why it is the soil friction angle is phi 1. So, that is phi 1, and the Kph is further represented at Ks. What is that Ks? That Ks is the punching shear coefficient, where Ks is equal to punching shear Why the punching shear coefficient is considered? Because in horizontal direction, I mean in the vertical direction, soil is punching basically. Because in the first layer you can see, because of your bottom layer is very weak, there is really a punching of this foundation in the soil, first layer. That means the soil is deforming along the horizontal line or the dotted line, along the dotted line, and it is punching. So, that is why it is considered as a punching shear coefficient Ks. Okay, now the QB is written, the bearing capacity of the bottom layer, that can be calculated by the as usual our bearing capacity equation. And then finally, I can write that my Ks is function of your Q2 and Q1 and phi 1. Now, this case which is represented in a chart form, where it is the function of phi 1 and your Q2 and Q1. So, obviously, it is a function of phi 1 and Q2 and Q1 also. What is Q2 and Q1? Where Q1 and Q2 are ultimate bearing capacity of a strip or continuous foundation with B under vertical load resting on surface of homogeneous thick bed of upper and lower soil. Okay, so what does it mean? That this Q1 and Q2 are the bearing capacity of a foundation resting on a homogeneous soil on its surface, where the vertical loading acting and the foundation is strip foundation. So, that means we consider these layers individually, and then we place the strip footing on the surface, and then the soil is homogeneous. That means, first we will consider suppose the first layer or the top layer or the upper layer, and then we place the foundation of a strip footing with B, and it is resting on the surface and the vertical, no incline load, and then the bearing capacity that we will get, that is Q1. Similarly, we will place the foundation on the second layer on the surface, and then vertical load, strip footing with a B, and the bearing capacity that we will get, that is Q2. Okay. So, I can write that my Q1, it is in the strip footing and it is resting on the surface. So, that Q1 I can write, this will be C1 N C1, because your it is strip footing. So, shape factor will be 1, and it is the surface, the second term will be 0, and there will be third term also, and that is half gamma 1 B n gamma 1, and in the Q2 it is C2 NC2 again half gamma 2 BNC2. Now, as I have considered the phi 2 is equal to 0, then automatically if the second layer is clay, now if C2 is 0, then Q2 will be simple, if phi 2 is equal to 0, then Q2 will be simple C2 NC2. But we are giving a general equation, that is why I have written that C2 and gamma means first term and the third term also, as it is in the surface, so second term is neglected. So, that means your if phi 2 is equal to 0, then you will get Q2 will be C2 NC2. Okay. So, now next part, this is the chart that where that we can determine these values. Now, one thing that how I can get the NC, N gamma, NC2, N gamma 2. Okay. So, these values I will get from the chart or the table given by Mayer of bearing capacity theories. So, note that this NC I or N gamma I are the Mayer of bearing capacity factors. Okay, so these are bearing capacity factors I will get from the table given by the Mayer of in the original Mayer of bearing capacity equation. So, that factors I can use here. So, now we can we have to calculate few things. What are the things we have to calculate? If you look at this equation QB I can get the from the bearing capacity equation, and then we have to calculate CA and this case. Finally, it is been represent this case we have to calculate, and we have to calculate CA. What will be these two values? Okay, other things we will get from the values which are available values. So, now this equation final form of this equation is slightly changed. So, that I am writing first that final form of this equation is Q u, or I should change the color of the pen. So, Q u will be Q b plus 2 C A H divided by B plus gamma 1 H square 1 plus 2 d A plus divided by H. Now, this K P H is converted to K tan phi, this is B minus gamma 1 H. Okay. So, this is my equation. So, how I will calculate the case? So, case I will calculate this by using this chart. So, where this for different phi, if I know the Q2 and Q1. So, I have already discussed what is Q2 by and Q1. So, and I will get the Q1 and Q2 by using these two equation. So, I will get the Q1 and Q2, and if I know the this is the Q1, this 2 by Q1 1.4, 0.2 and 0, and as the upper layer is stronger layer. So, that means definitely Q2 should be equal to or less than Q1. So, that is why these Q2 by Q1 are equal or less than that. Okay. So, this is the equation, and then I will get the K's value corresponding to different phi 1 value. Okay. And CA by C1, C1 is the cohesion of the first layer. So, this is the C1. Similarly, I will get Q2 by Q1, and from this chart I will get the CA value. So, this way I can get the CA value as well as the K's value. Clear? Now, the next part is that if your H is very large. Okay. So, H is very large. In such case, that means here we have to put one limit. Suppose if your H is very large, that means all the failure zone is within that H. So, that means the bearing capacity of the foundation in such case will be the bearing capacity of the footing if I put it on the first layer itself, where the depth of the layer is very high. Okay. So, that means in such case I will get a bearing capacity value if your H is very large is your Q ultimate is equal to Q top. Top means the top layer bearing capacity. So, that I can calculate CNC 1 plus Q NQ 1 plus half gamma 1 B N gamma 1. Okay. So, here I am not giving other factors or other bearing the correction factors, all those things. I am deriving the basic equation with only the coefficients, and we assume that all the other factors are 1 and it is for strip footing. So, that is why this is the equation. So, that means this is the bearing capacity if the foundation is resting on the top soil only, where the bottom soil influence is not there. So, that will be the maximum bearing capacity of this foundation. Now, if the bottom soil influence is there, because as the bottom soil is the weaker soil, so then if the influence of the bottom soil zone increases, your bearing capacity will reduce. So, the maximum bearing capacity you will get if the whole influence zone is within the first layer, because that is the first layer is a stronger layer compared to the second layer. So, you will get maximum bearing capacity if all the influence zones of the foundation is resting within the first layer or within the H. If this is only possible if H is very large. So, that is the limiting value, your bearing capacity cannot be greater than that value. Now, if your because the lower layer is the softer layer or weaker layer, so as the more influence zone is covered within the lower layer, your bearing capacity will be decreased. So, that is why there is a limit is placed. So, finally, we can write that Q u is equal to Q b plus 2 C A into H by B plus gamma 1 H square 1 plus 2 D F by B K S tan phi divided by 2 B, this is H B, then minus gamma 1 H, that should be less than equal to Q t. Okay. So, Q t I will get from this equation, and because this is the limiting value, your this Q u cannot be greater than Q t. Okay. It can be equal to Q t, and that is the limiting value. It can be either equal to Q t or less than that, it cannot be greater than that. So, this is the limit which is placed. Now, this equation is for the strip footing. Strip footing, now if I convert it to for the rectangular footing, then the Q b will be Q u will be Q b plus 1 plus B by L into 2 C A H divided by B plus gamma H square 1 plus B by L 1 plus 2 D F by H K S tan phi divided by B minus gamma 1 H, that should be less than Q t. So, this equation is for the rectangular foundation. Or if you put B is equal to L, then it can be used for the square foundation also. So, and the similar way this type of foundation we can use it for the square footing also, circular footing also. Now, how I can use the circular footing? In such case, QU will be QB plus two gamma A square 1 plus 2 df H S K S tan phi divided by B minus gamma 1 H, that should be less than Q T. Now, here your Q B will be equal to 1.2 C 2 N C 2 plus gamma 1 d f plus H for phi equal to 0 degree, and Q T will be equal to, that is for the top layer. So, gamma d f in Q 1 plus 0.3 gamma 1 B in gamma 1. So, here C is equal to 0. So, for that means your layer 2 or I should write, this is the layer 2 which is clay and layer 1 which is sand. So, this equation is valid. Now, this is for circular footing. Okay. Now, here there is a term S. Now, this S is a shape factor and can be taken as 1. So, that means we have given the equation for 3 cases. First one is the strip footing, where the QB equation is given, that QB I can calculate by okay. So, QB I can calculate by using these equation for clay soil, and for general soil also you can calculate. Now, here this is for the rectangular footing, where you have to calculate the QB, and remember that when you calculate the QB for rectangular and strip footing, there also you have to apply those shape factor corrections. Okay, but in the circular footing it is given QB is 1.2 C2 NC2 gamma 1 df plus H, and QT is that for the circular footing also it is given, and is for the circular footing it is assumed that the top layer is sand and the bottom layer is the clay. In other cases also we have considered that the top layer is your, because phi 2 is equal to 0, bottom layer is equal to clay and the top layer is equal to sand. But here when I calculate QB here, I have considered strip footing. Okay. Now, in the rectangular footing part, there is also QB. So, remember that when you calculate QB for rectangular footing, you have to apply the shape factor. Okay. So, like this the way it is been done in this equation. Okay. So, remember that, and the circular one it is been already given. So, these are the 3 equations for strip footing, rectangular footing and the circular footing for 2 layer soil, and mainly the first layer is the stronger and which is sand, and second layer is weaker which is clay. So, this is the condition we have discussed. Now, what we will do? We will now solve one problem and we will see that how we can calculate the value. And again, as I was talking about that for the QB calculation for rectangular footing, that and the QT calculation, because this QT is calculated without considering shape factor. So, this is also valid for the strip footing. So, now let me write these things, that for the rectangular footing. So, as I mentioned that these QT will get for the strip footing. For rectangular footing, foundation, now QB is equal to C2 NC2 into SC2, shape factor you have to apply, plus gamma dF plus H NQ2, then SQ2 plus half gamma 2 B n gamma 2 S gamma 2. Now, this is in general equation. Now, if your phi 2 is equal to 0, then QB will be C2 NC2 SC2, then plus your this is gamma dF plus H into NQ equal to 1. So, this will be your SQ2. Okay. So, because your NQ is equal to 1 in such case, so SQ2 that also you have to use, and then gamma dF plus H. Okay. So, now for the rectangular foundation again, if you write that, how you can write QT, that QT again I can write QT is C1 NC1, then shape factor you have to apply SC1, then plus gamma 1 dF, then NQ1 SQ1 plus half gamma 1 B n gamma 1 is gamma 1. 1 is for first layers, 2 is for second layer. Now, if your C1 is equal to 0, then QT will be, this C1 will be 0, gamma 1 dF, NQ1 SQ1 plus half gamma 1 B n gamma 1 is Q S gamma 1. Okay. So, this is the expression. So, now I will take different example problem, and then what are the cases are possible. Okay. So, the cases that possible, if I take, suppose this is my top layer and this is my bottom layer. Okay. So, first case, the case 1, the top layer that I will discuss is the stiffer clay, because I have considered the top layer is stronger compared to the bottom layer. The top layer is the stiffer clay, bottom layer is the softer clay. Okay, this is my first case. Second case, I can write that this is stronger sand, strong sand, and this is softer clay. or soft clay. So, that means here it is both are cohesive soil. Here it is first layer is friction soil, sandy soil, second layer is the first layer is the cohesionless soil, second layer is the cohesive soil. In the first case both the soils are cohesive soil, and in the third case I can write that the stronger sand and weaker sand. That means both are cohesionless soil. So, these two I have already derived, because I have considered that this derivation, this gamma 1 minus gamma 1 h, which is that form which is applicable if it is a strip footing and it is resting on the clay soil. So, you know that. Then the stronger sand and weaker sand is also possible, and I will discuss another case, fourth case, which is a case which is not in these cases. So, that fourth case I will discuss, where my soil is the first top layer is the loose sand, and the bottom layer soil is the stiff clay. So, this is again phi c, but this will not similar to the case 1, 2, 3. So, case 1, 2, 3 is one group and case 4 is another group, because in case 1, 2, 3 all the cases the lower soil is weaker than the stronger soil. Okay. So, and the derivation that I have done is valid for first 3 cases only, where the weaker lower soil or the layer 2 is the weaker soil and layer 1 is the stronger soil. But the fourth case is these equations are not valid for the fourth case. The fourth case I will discuss in detail later on. Let me first solve the problems for the first 3 cases and then I will discuss the fourth case. Okay, so, now let me discuss the first problem, that rectangular footing of size 2 cross 2, 2 cross 3 meter is placed at a depth of 1 meter in a stronger clay. So, first one is it is resting in a stronger clay. The thickness of the stronger clay is 2 meter. Okay. The water table is at the ground level. A softer clay layer is located below the stronger layer. The undrained cohesion of the stronger and the softer layer is 100 kPa and 40 kPa respectively. The saturated unit weight of the stronger and the softer layer is 20 kilonewton per meter cube and 18 kilonewton per meter cube respectively. Both the unit weight for the stronger and soft layer are considered same for this particular problem. Determine the ultimate bearing capacity. Unit weight of the water is taken as 10 kilonewton per meter cube. Okay, so, now your problem is, it is both the soil are cohesive soil. Okay. So, now your foundation is resting at a depth of 1 meter. Yeah. So, your depth of foundation df is 1 meter, the width of foundation is 2 meter and the thickness of the stronger layer is 2 meter. That means, this is my stronger layer whose thickness is 2 meter. So, my h value will be 1 meter. The thickness of the stronger layer below that foundation will be 1 meter and there is a weaker layer at the bottom. So, this is C 1 and gamma 1, this is C 2 and gamma 2, because phi 1 and phi 2 both are 0 and water table is considered at the ground. Okay. So, now let me solve this problem, that my that is gamma 1 Oh, saturated, no, it is not same. For the saturated unit weight for the stronger and softer layer is 20 kilonewton and 18 kilonewton. So, both are different. For stronger layer it is 20 kilonewton saturated unit weight Newton per meter cube, and softer layer it is 18 kilonewton per meter cube. So, submerged unit weight for layer 1, sub 1 will be 10 kilonewton per meter cube, and for layer 2 submerged unit weight will be 18 minus 10 8 kilonewton. This is sub 2 8 kilonewton per meter cube. Okay. Now, first it is a rectangular footing. Let me write the general equation. So, that general equation is this one for the rectangular footing. This is the general equation. Okay. So, let me write that general equation, that Q u will be Q b plus 1 plus b by L, then 2 C A H divided by B, then plus gamma 1 H square, 1 plus B by L, then 1 plus 2 D F by H, then K S tan phi 1 divided by 2 minus gamma 1 H. Okay, so, all these equation remember that this is tan phi 1, okay, because it is in the first layer. So, this is all the equation, it is tan phi 1. I do not know whether I have written or not. So, yeah, it is tan phi 1. So, I maybe missed that, you remember that this will be tan phi 1. So, this is the basic equation. So, next class I will solve these problem, okay, because I have taken the I have written the basic equation, all the properties are given. So, next class I will first solve this problem, and then I will discuss about the other cases that I have discussed in this class. Thank you.